Hello all. Uh, let's continue our discussion on current voltage characteristics of BJT. Last time we met, we discussed about the various current gains. Now let us talk about the output characteristics. So particularly it has the relationship between the currents and the terminal voltages in the junction. So let us very quickly draw the electron concentration. Let's once again take the example of uh, N, P, N transistor and look at various carrier concentrations at various, this is VBE and this is VBC, right, under all these conditions. So this will be VBC, this is VBE. So now let us see what happens, right? So there are few conditions. Let's take the first situation where VBE is positive and variable and VBC is negative. Okay. So this is the normal mode of operation. So now let us look at how the junction carrier concentrations will be, right? So let us say this is the depletion width of the emitter base junction, and this is the depletion width of base collector junction. Base collector junction is negatively biased. So basically you have, as our previous discussion, this is 0 and this is W, right? And this is positive bias, right? So basically your electron concentration or the whole concentration here will drop like this, and the electron concentration, depending upon, let us take our initial electron is here, then you will have an exponential decrease, right? And it depends upon and this point. So n of 0 is actually e power or np naught e power qv by kt. This we saw, right? Depending upon the v is vbe, and at 0, at reduced potentials, you will have something like this, and this is the case in vbe equal to 0. And as you increase the positive potentials, you increase the carrier concentration in p type. So this is p type base, right? And this is the normal mode of operation. So, and at this point, whatever is the carrier density which is present, it is being drifted by this huge depletion width to the collector and collected back, right? So this is the most simplest normal active mode. Now let's look at the second case when we have VBE is positive again and VBC is negative and increasing. What happens under this case if I start increasing VBC, we will get the same thing. I'm not going to redraw the base emitter side, which is obviously the same. Now we know that as we increase VBC, the negative the depletion width will increase, right? So this is, let's say, width 1, this will become width 2. And also remember, collector junction is more doped, so most of the depletion width falls on the collector junction, but the base is also not so heavily doped, right? So as we increase VBC, we are going to have more and more depletion in the base region, right? And because VBE is not being changed, we will get some carrier density here. This side is going to be like this. So this guy is going to drop, and if it drops to some value here, on increasing VBC or on increasing the negative bias, it goes further drop, right? And this is the case when VBC is 0. that is, you just have, if you don't have really if you are not depleting, I mean if you're not applying any reverse bias, you just have some depletion with this, the built-in potential, right? As you increase the reverse bias, what you do is you reduce the minority carriers further, right? So as you increase the depletion width, you actually reduce the minority carrier below the intrinsic minority carrier concentration, correct? So the more you dip, the more it falls down. So basically this is W1, W2, W3 all increasing with respect to this. This has to be remembered in our discussion that we will have. So this is just to have a feel for what kind of depletion width we have at different bias potentials. The third situation is when VBE is positive and VBC is positive. So this is what we call as saturation, because both these junctions are forward bias, right? So let us draw this. It's an interesting situation. This is the depletion width. Yeah, I'm going to draw it a little bit smaller. Again, in this side also, remember both of them are positive, right? So it has to be small. And one has to remember that you have some carrier concentration N here, NP naught. And because of the fact that the base collector is also being forward biased, you also have heavy injection on the from the collector side. So you have electron injection from the collector side and you have electron injection from the emitter side. So the base current actually is severely reduced, because as you see that the current is mostly dominated by diffusion, right? And if there is no big gradient, right? So as you increase the collector bias, as you increase the forward bias in the collector base junction, you are increasing the injection into the base, so that you will very quickly remove the carrier concentration difference in the base, leading to very low diffusion currents, right? Now as you reduce the forward concentration, the carrier concentration in the base can reduce. This will lead to higher currents. IC greater than 0, this is IC equal to 0 under some bias conditions. This width is smaller than the depletion width we previously saw, right? So this is the situation of saturation. Next, let's look at the situation when both the base emitter and the collector base are both negative. Base collector are both negative. Then we have the cutoff, and both of them are reverse bias, so we have very low current. And this is the fourth region of operation, right? But other than this, there is some interesting situation which will crop up when we have very low bias and one of the terminal is turned off, right? So basically in the same emitter base configuration, let's say we have an emitter base collector. So let us take a situation where the emitter and base are both grounded, right? And we push some very small current through the collector. So now you can see that because both of them are grounded, right, and you have some current through the emitter as well as the base, you have some, let us take the depletion width in the base is here, the depletion width in the collector here. You have some gradient in the electron configuration. This is NP naught due to the current from collector to the emitter, right? Now under this situation, let us assume that the emitter is open circuited, right? We remove the emitter. If the emitter is open, you can see that this is a very simple collector base reverse bias junction, and because of the fact that the emitter is not connected and there is no current, right? So there is no gradient in the carrier concentration in the emitter. So this will lead to a carrier concentration which will resemble what we have seen in the depletion, similar, I mean, in a simple PN junction depletion width, right? And this will be much smaller than the situation where emitter and base were both connected to the ground. So this is when emitter is open. The other situation that you can imagine where the emitter is grounded and the base is open, right? The situation when the base is open. So in this situation, you can clearly see what happens is you have reduced the recombination in the base because you do not have any base current, right? And you will have a higher emitter collector current in comparison to when the situation where emitter and base are both grounded or the collector being open. This is the situation when base is open. So because of the fact that the gradient in the current and the current concentration determines the total current in the junction, right? So this particular aspect, as we saw currently, is useful in understanding the output characteristics that we will see soon. Okay, so we will study the output characteristics in two different configuration. The first configuration is common base characteristics. It looks like this. So because it's a common base, okay, let's take this BJT. We have an emitter, base, collector. Base is grounded and you have some potential here VE and we have some potential here VC, right? Under this situation, if I draw the output collector current as a function of the collector base potential V, it turns out to look something like this. It remains almost constant without a slope. I think I have drawn this with some sort of a slope. And if VCB turns negative, right, we can see that if the collector junction is lesser than the base, you can see that the base collector junction becomes forward biased, and when it is forward biased, as we previously see, that the current has to radically drop, right? Why? We saw this, right? So this is 0 W, and if this is the base, as the base collector junction is forward biased, you will start to have more and more injection. If this is the injection in the emitter side, NP naught E, you have NP naught from the collector. As long as this level is smaller than the emitter side, you have some gradient and you have some current. But if these levels, if the electron level from the electron injection from the collector increases dangerously close to the electron injection from the emitter side, now you have no gradient and hence no diffusion current in the base, and hence the current drops very fast to 0, right? And if you start to make it any more negative than this IC equal to 0 point, you can see that the current will start flowing on the reverse side, right? So basically this region is called as saturation, right? And here you have IC almost equal to IE. So let's say if this is IE is equal to 0, this is IE equal to 0.1, so this value is 0.1, this value is P2, right? Now what happens if I increase the reverse bias dangerously high, right? So there are two things which can happen. Now as I increase the reverse bias, as we saw previously, the depletion width will increase, and if the base width is so small, you reach to a point what is called as punch through. punch through happens when the depletion width from the base collector reverse bias reaches the emitter base junction. So basically your base is now completely depleted and the collector and the emitter is joined together. Then your collector current kind of shoots radically faster, or you have an avalanche breakdown, right? And avalanche breakdown we know happens at reverse bias because of the potential, the distance with which the carrier difference with the distance at which the carriers are accelerated, right? So basically that will lead to enhanced carrier velocities, leading to impact ionization of further carriers and so forth, right, leading to avalanche currents. So that will cause breakdown at higher reverse bias potentials. And the common base is actually characteristic of the point that you have gain of almost unity. IC is almost equal to IE, right? And under these situations you have very high output impedance, which is useful for many circuit applications. The second configuration that we will see today is common emitter configuration. By the way, this is a region where the collector or the emitter current is zero, and we saw from this situation that when the emitter current is zero, you have almost among the lowest carrier concentration in the base, leading to almost lowest collector currents, in the fact that when even emitter is zero. We will see in the common emitter current configuration that you will have some current which is larger than the previous case when the base current is zero. So in the common emitter configuration you have emitter, base, collector, right? And the emitter is grounded and you have some potential at the collector VC, some potential at the base VB, right? And in this situation you can clearly see that VCE is a summation of VCB plus VBE, right? And when BBE is forward bias, you have a VBE value which is very small. For a silicon diode, we know that at forward bias it's about 0.7 volts, right? So most of the VCE that we apply drops directly to VCB, basically increasing the reverse bias in the base collector junction. A typical common emitter configuration looks like this. When the base current is zero, you have a small but non-negligible collector current, right? As you increase the collector potential, right? Now the fact that as long as this collector potential is smaller than the base potential, right? Let us draw that line somewhere like this. As long as the collector potential is within this region, you can see that the base collector junction will be forward biased, right? So you will have saturation region, because you can see that as you reduce, so basically as you fall to the saturation region, the current starts to drop radically deep into saturation, right? As you start reducing the collector potential or increasing the base potential with respect to the collector potential, either way it's the same thing, right? As you start increasing the forward bias in the base collector potential, you will have the current to fall down drastically. That is the similar thing that we saw in the common base configuration as well. But the most important aspect of common collector configuration is the fact that IC does not or is not constant with respect to VCE. So there is a slope in these lines which is non-zero. So the slope can be calculated as like this, right? So basic, okay, before we go to calculation of the slope, we will qualitatively see why there exists a slope, right? So we have this junction, and you can see that as I increase the collector potential or if I increase the reverse bias, the actual depletion width increases, right? But then because I'm not changing the base potential, the electron injection remains the same, right? And as I increase the reverse bias, we know that the electron concentration at the edge of the depletion with np of w reduces with vce, right? So basically I increase the gradient as I increase the collector base potential. As I increase the reverse bias in the base collector potential, I increase the gradient in the electron concentration, causing the current to increase, right? So this is the reason why you have a non-zero slope in the common emitter configuration. Now to calculate this slope, we use the expression that we previously derived, which was q dn ni square a by integral 0 to w. So this, I use this expression because we assume that the base is not uniformly doped, because we wanted to have some sort of a drift, giving you better base transport factor and so on and forth, right? So now if I do dou ic by dou v cb, I will get minus aq dn ni square e power. Now it's easy to see that the only thing that changes in this expression when I change the VCE or when I change the VBC is just the width, right? And this will turn out to be, I think I will have another NA of W. This will turn out to be minus IC NA of W by PCB. Of course, this is, this is Q, right? So Q is the Gamal number that we previously saw, but then for this purposes, this expression is written as minus IC by VA, and VA is called as the early voltage, and this phenomena of non-zero slope in IC versus VCE was discovered by Early, and this is called as an early voltage VA, and VA turns out to be integral 0 to W NA of x dx by now you can very easily calculate this, because from our previous assumption that QB, this is the total charge or dopant integral in the base, and if you do this dQB by dVCB, we get Q NA of W dW by dVCB, right? Now this number is some capacitance, right? It's a change in some charge by change in the potential applied, and it's easy to see that, let's say this is the width, this is the base, right? And changing, so let's say this, and this is W, and Q is an integral of charge densities in this neutral region. But typical depletion capacitance, or the capacitance as we discussed like this, is the charge in the depletion width, right? But then you can see that any change in charge in the depletion width will change this W, which will in turn change the QB, right? So they are all equally related. So this expression dQB by dVCB is approximately or closely related to the depletion capacitance in the base emitter, sorry, in the base collector junction. So I'm going to replace this QNA of W dW by VCB, right? So if this is substituted, I can easily see that it's actually a modulus of VA. Modulus of VA is basically QB by CJC. So the actual early voltage VA is proportional to the total doping, the integral of total doping density in the base, and inversely proportional to the depletion capacitance in the base collector junction, right? So in the characteristic that we saw, something like this, right? It can be proved that the slope is same as the intercept in the x, so the slope was what we saw is VA. It can be proved that if the base width is small enough, you will have this as VA, that is its intercept in the x-axis, right? And if VA is large enough, then we will see that this slope is small enough, because we saw the slope is inversely proportional to this VA, right? This is 1 by VA, right? And how do we obtain large enough VA? We obtain large enough VA by changing the total dopant concentration in the base. So you have to increase the total dopant concentration in the base to get a very large early voltage. To get a large early voltage, you need a large QB or base doping density. Now, why a large VA is necessary? That comes from the fact that you want a small DIC, that is for small output impedance, output conductance. Dou IC by dou VCE, for small output conductance you need a large VA, and the large VA is obtained by increasing the base doping constant, right? But then we also saw that JS is inversely proportional to 1 by QB. That means IC is inversely proportional to 1 by QB, right? So increasing the base doping density will reduce the collector current as well. So this is a trade-off that most designers with BJT have to face, that if you want to increase the collector current, you have to reduce the base doping integral, and if you want to have a very high output impedance or low output conductance, you need to have a very high base doping concentration, right? So with this discussion we will stop now, and next time we meet, let us discuss non-idealities in BJT and some RF and microwave characteristics. Thank you.